In this video, we'll be finding out the center of mass of a right angle triangle, which is right angled at O. We can take that as the origin. Let's say that the base of this triangle is of length A, and the height of the triangle will be length B. So, and let the triangle, of course, have a mass of M. So what we should start off by doing is define what our elementary particles are going to look like. Here I've considered extremely thin triangles. So our elementary unit is going to be a triangle. And we have to integrate infinitely many elementary triangles and constitute the entire triangle. I mean, infinitely small rectangles, my bad. So what we're going to do is, so first of all, we already know that the tiny rectangle is going to have some mass. And the tiny rectangle is going to have a tiny mass. So let's start off by defining exactly how much mass it's going to have. So dm is equal to, this dm can be given by the ratio between the areas of the rectangle itself and the entire triangle. So the area of the rectangle is going to be dx into the height of the triangle. Let's just consider it to be y. We're considering this rectangle to be in a very general location at a distance x with a height y and a thickness of dx. So x dy, y dx divided by the area of the entire triangle is half AB, and we can write the 2 up instead of it being in the denominator into the mass. So this is the value of dm that we got. And so first let's find out where the y center of mass is going to lie. So the y center of mass is going to lie somewhere approximately over here, right? It feels like this might be an appropriate spot because, like, if you visualize it well enough, we can see that the mass kind of lies, like half of it lies on top, half of it lies below. So how would you find this? So the y center of mass can be given by integration of y center of mass, where this ycm, let me just call it y prime cm, where y prime cm is the center of mass of the elementary particle that we've chosen, times dm integration dm. And we know integration dm is just m. So for a rectangle, let's say this is a rectangle, right? The center of mass is going to lie in the middle of the length. So similarly, we can say that the center of mass of the y prime, the center of mass of the elementary rectangle, is just going to lie at a distance of y by 2. And dm, as we found out earlier, is just 2 dx y times divided by ab times m divided by m. And the m and m just gets cancelled. The 2 gets cancelled. AB is a constant which can be taken outside. So you get 1 over AB times y squared dx. Integrating y with x seems a little off. So in order for this to make sense, we must establish a relationship between y and x. How exactly would you do so? So if you observe the hypotenuse of the triangle, what exactly happens is that the hypotenuse intercepts the axis at A and B respectively. So by the intercept form, the line intercept form, what we get is x over a plus y over b is equal to 1. So this is the line that represents the hypotenuse. And simplifying this, you get bx plus ay equals ab, and y is equal to minus b upon a x plus b. So this is what you get. And what we can do is, we can differentiate this. Instead of replacing the entire y into this and squaring it, it's a lot of calculations. Instead, what we can do is, we can write dy by dx and differentiate this. You just get differentiation of minus b by into x, which is just minus b by a. And rearranging this, we get dx is equal to minus a dy upon b. And we can substitute this over here, and you basically get 1 over ab integration of y square into minus a by b dy. And the a over here can cancel the a over here, and you get minus 1 over b square integration of y square dy. And here the limits are going to go from b to 0, where b is the length of y. Like, let's say that x were to shrink a lot. So initially y was the entire length, which is b, and as x increases, your y becomes 0. So evaluating the limits and integrating it, you get minus 1 over b square into y cube upon 3 from L to 0. And let me just write the answer over here. What you get is minus 1 over b square into minus b cube upon 3, and this simplifies to b over 3. So your y center of mass is b over 3, and it makes sense. It lies somewhere a third of the distance from the origin. And now we have to repeat the same procedure and find it for the x center of mass. We could take this y is equal to minus b by ax plus b and substitute it out here and get a very complicated integration. Not very complicated, but it's still lengthy, isn't it? So instead of doing this, we can look for symmetry in the equation itself. Notice how, if we were to repeat the process all over again, many terms would be common. So instead of writing y center of mass, we can write x center of mass over here. Instead of y prime over here, we can write x prime over here. And wherever y is, you can just safely just substitute x, and your dx's with the dy's. And what you'll be left with is x square dy. And again, now we can rearrange y in order to find, we can rearrange this to find that dy is equal to minus b over a times dx. So now we can substitute this into that, and you get 1 over AB integration of x squared, and dy is basically minus b over a dx. Here b gets cancelled, so you get minus 1 over a squared, and integration of x squared dx is x cubed upon 3, and x goes from 0 till all the way till a. So from 0 to a. Hold on. I'm sorry, it goes from a to 0, a to 0. So basically, when you're changing this up, you must also change the diagram. So x is somewhere over there, and what we are doing is take this as your y-axis, of course. So you'll be going from so you'll be going from a to 0, my bad. So what you get is a to 0. Yeah, so by solving it, you get minus 1 over a squared times minus a cube upon 3, which just simplifies to a over 3, and a over 3 lies somewhere over here, and you get the center of mass is located at a distance of a by 3 comma b by 3. Thank you.